Okay, so let's go ahead and start. So thank you all for joining the New Directions in Statistics, Machine Learning, and Optimization workshop at the IAS. So it's a pleasure to have Stefano Ermon speaking today. So Stefano has just done a lot of great work in AI and reasoning with various applications to social good, which is particularly relevant right now. And another line of his work, which is particularly exciting, is on probabilistic generative models, which I personally find pretty exciting because they kind of legitimately learn a distribution in a way with a proper scoring rule. And I think he's going to talk more about this. So it's definitely an area close to my heart, and I'm looking forward to his talk. In terms of questions, definitely just go ahead and type your questions in. I'll be moderating. And I think some of the questions actually make sense to just interrupt Stefano and ask him, because I think it'll just make it a bit of a nicer format. So without any further ado, let's go ahead and introduce Stefano.
All right.
So I think you want to share your screen and then just go ahead and start.
Yes. All right. So is this working?
Yes, at least for me.
Can you see the screen?
Yeah.
Perfect. All right. Thanks for the introduction, and it's a pleasure to meet you all virtually. And today I'm going to be talking about some work that I've been doing with my students, mostly Yang Song and Shenjia, on learning generative models using score matching. Right. So, and yeah, as Sham said, I mean, I'm happy to take questions throughout the talk. I'm still learning how to give these remote virtual talks. And so, but I think we can keep it interactive. I think it's going to be a better experience for everybody. All right, so in the last few years, there's been a lot of progress in learning generative models of complex objects like images, text, video, music, graphs, even molecules. Pre-training on a language model, which is basically a generative model of text, has become widespread, and it's kind of like needed if you want to get state-of-the-art results on a number of benchmark tasks. And these models, these generative models of texts, they work reasonably well. I tried just for fun to see, playing around with the GPT-2 model and see how it would complete a sentence starting with the generative models cannot, and see how it would complete it. And the result I got is generative models cannot be considered to be an adequate representation of reality. So it's just pretty cool. It looks like generative models know what they don't know. But I guess more broadly, I think I'm excited about generative models because I think they are a very principled way to think about unsupervised learning. If we want to go beyond this idea of training large neural networks using lots of labels, I think we need to figure out a way to extract structure from unlabeled data. We've seen progress in NLP, and perhaps we can do the same on other modalities like images, satellites, video, and so forth. Right, and so there are kind of like two main classes of generative models. The first one are implicit models, where basically the model represents directly the way in which we generate samples, the sampling process itself. So for example, you might start from some random noise, sample from a simple distribution, which gets transformed by some function, for example, a neural network, to produce a sample, maybe an image. And think of all the sampling process that we can get, and we change the function that we apply to this base distribution. For example, we can parameterize it using various neural networks. And these models have been shown to work quite well, like GANs. One issue is that the probability distribution over the outputs that they generate might be intractable or even not well defined. And what this means is that we cannot train them by maximum likelihood. And you typically need to train them using some kind of adversarial procedure where there is a mini-max kind of game between a generator and a discriminator, and this can be unstable. It's hard to understand, and it's also difficult to do some principal ways of comparing different models on the same data. Now, another widely used class of models is based on our explicit models, where basically the key object that is being represented is directly the probability density or the probability mass function over the object that we want to generate. And this includes classic graphical models like Bayesian networks, undirected models like Markov random field. The challenge of this approach is that being able to define very complex objects, complex probability densities or probability mass functions that we can use to represent, let's say, and model real-world probability distributions, and at the same time tractability. We need to be able to evaluate P of X efficiently if we want to train by a maximum likelihood. And so what I'm going to do in this talk is I'm going to discuss a different kind of approach where instead of working directly with the probability density function, we're going to work and we're going to look at the gradient of the log density with respect to the input dimensions, right? And so just to be, this is often called a score. And just to be clear, this is not the gradient with respect to the model parameters. This is really the gradient with respect to X, with respect to the random variables that you're trying to capture, right? So if P of X is a distribution over images, this is a gradient where each component is a partial derivative with respect to each pixel. Right? And so just to get some intuition about this object, because it's going to come up for most of this talk, we can look at what this thing looks like for a simple distribution, like a mixture of two Gaussians. So we have two Gaussians here. Can you actually see my?
Yes.
Okay, great. Was there a question?
No, just some technical glitches on my end.
Okay. But you can see my pointer.
Yes, I can see it.
Perfect. Okay, good. So we have a mixture of two Gaussians here, where this component has a higher weight. Here, the color represents the probability density associated to each point. We are in 2D, something relatively simple, and we see that the gradient, that the score is a vector field, where at every point, basically the gradient is a vector, which will basically point us in the direction where the log density grows the most, right? So it's pointing towards the two modes of the distribution. And so, like, if you like physics analogies, this is kind of like going from modeling a physical system, like two charges in terms of an electric potential, to modeling the same physical system using an electric field. So they're kind of like the same thing, but it might be useful to use one view or the other for some kind of tasks. Right, so why would you want to use scores? There are a couple of reasons. One is that, as we discussed before, when we work with probability density functions, these objects, they have to be normalized, right? So if you imagine like a mixture of two Gaussians, you can change the means, you can change the standard deviations, but at the end of the day, the object that you get, it has to integrate to one. On the other hand, if you look at the score of this one-dimensional distribution, it's basically a function that doesn't have any constraints. And so what this means is that we don't need to impose all kinds of constraints on our neural networks, for example, to make sure that we get a valid density, because basically any function in this case will define a valid score and therefore a valid probability density function. Another example where scores can be useful are energy-based models. So here the idea is that we want to define a probability density function, p theta of x, in terms of an energy function, which it could be, for example, a neural network that takes as input x and produces a scalar, a number f theta, which is the object that defines the underlying probability density function using this formula here. So we see that the probability density associated to a point x is e to the minus the energy, is proportional to e to the minus the energy at that point. And what we see is that in order to, which we use an exponential to make sure that this object is non-negative, but then we need to make sure again that this object is normalized, that it integrates to 1. And so we have to divide by z theta, by the partition function, to make sure that for any choice of the, let's say, the parameters of the energy, the parameters of the neural network, we get a valid probability density function that integrates to 1. Now, the advantage is that this object is very flexible. You can basically choose any, let's say, neural network for your energy function, and this will define a valid probability density function. The challenge is that evaluating the partition function is hard. It involves an integral over the whole space of the numerator of this expression. And in general, that because of the cost of dimensionality, that's an expensive procedure. And what this means is that if we say have some data distribution, p data, and we get samples from it, and we want to choose our parameters to maximize the average log likelihood assigned to samples from this data distribution, when we take the log of this expression, we get two terms. We get one term which is just the actually there's a typo here, that is just the energy, which is easy to evaluate, and then the problem is that there is this term, which is the log partition function, which in general is hard to evaluate because it requires us to integrate the unnormalized probability over the whole space. Now, the nice thing about the score of this energy-based model is that if we look at the gradient with respect to x of the log density, we see that we get two terms. We get the gradient with respect to x of the energy function, and then we get a gradient with respect to x of this log partition function, which does not depend on x anymore. It's just a constant. And so that term is 0, and basically it goes away. And that's kind of like the key advantage of the score, is that the score does not depend on this intractable partition function, but it only depends on the energy function, which is something we know how to handle. And so what we can try to do is we can try to learn this model, this p theta, this distribution, by working directly in terms of the scores, right? Instead of using maximum likelihood, what we can try to do is we can try to choose parameters in our model data such that the vector field of scores that we get in our model is close to the vector field of scores corresponding to the data distribution, right? So instead of working with the electric potential, kind of like we're working with the in terms of the electric fields, if you remember that analogy with physics. And so that's kind of like the idea. We're going to try to choose parameters such that the vector field of gradients that we get corresponding to our model is as close as possible to the vector field of gradients that we have under the true data distribution. And because we work with scores, this can be more efficient because we don't have to worry about this intractable partition function up here that we don't know how to compute. Right, and so that's kind of like the one application of this of using scores. We might think about a situation where there is an underlying data generating process. We get to see some samples from this data distribution. We have a training set of samples from this p data, and the goal is to come up with a model of the vector field of scores. This is a vector valued function where at every point it will give us this gradient, this vector, which is basically the direction in which the log density grows the most according to our model. And the idea is to try to make sure that this vector field of scores that we're estimating is as close as possible to the true underlying vector field of scores of the data generating process. But we don't know p data. The only thing that we know is this training set of samples that we get from the data generating process. Right. So more formally, the problem is as follows: we're given IID samples from a data distribution, and for simplicity, I'm going to now call it p of x. And the task is to somehow estimate this vector field of scores for the true underlying data generating process. And the way we do it is by introducing a score model, which is a vector valued function as theta. Given any x, it will give us the corresponding gradient estimated at that point. And the question is, how do we compare the true underlying vector field of scores with the one produced by our model? And one way to do it is to just basically overlay these two vector fields. We can look at every point what is the true underlying gradient and the one estimated by our model. We can look at the difference, and we can, let's say, average over the whole space. That will give us a notion of how far away is our estimated vector field of scores with respect to the true one. And so this defines the following objective function, where what we're doing is we're averaging over the whole space based on, so we're taking an expectation with respect to the true data generating process P of x, and at every point we look at what is the Euclidean distance between the true vector, true gradient at that point, and the one estimated by our model at that point. And this is called the Fisher divergence, and it has good properties. It's easy to see that if we have the right model, so if every point our estimated gradient is actually equal to the true gradient, then this Fisher divergence is obviously 0. And if the Fisher divergence is 0, you can show that the distributions are actually the same. So if you are able to minimize this objective function, then we're going to be able to learn the true data generating process by fitting this model, which is working directly at the level of scores. All right, now before I talk about how to actually optimize this objective function, maybe I'll stop a little bit and see if there are any questions.
Well, I have a question. So S theta is what you want to learn here, right?
Yeah.
And then if you had it, then presumably there's some way to reverse engineer P of x or get samples from it. Okay, and then and of course optimizing this, just to be clear, that we don't know the grad of P of x, because log P of x is the truth, so we don't know that grad. Okay, that was a question.
Yeah. That's what's going to come up next. Basically, perfect segue into the next. What happens next is, well, how do we deal with this term that we don't know, and then how do we go from how do we use this S data to actually, let's say, sample from it or do some kind of inferences based on the model. Yeah, great question. Any other question?
Nope, we're good.
All right, so let's continue and let's talk about, first of all, how do we even evaluate this objective function?
Sorry, there was a question. So I think it's pretty fast. So is there any prospect of this method scaling to high dimensional input spaces of the sort encountered in actual applications like images? From the moderator, I would say hang tight, because I've seen some pretty spectacular demos from Stefano. So I don't know what he does, but I imagine we're going to see it pretty soon.
Yes, as a preview, we'll show you that it works on images, and that actually gives you samples that are comparable to the ones you can get from GANs, from generative adversarial networks, which I think is exciting because this kind of approach has not been engineered as much as GANs, and you can still get really, really good samples. And it's more, I guess, as Sham was saying, it's based on a scoring rule. So I think it has some nice properties. You can compare models. You can do things that it's more stable to train. You can actually, like you're optimizing a proper divergence. And so I'm pretty excited about this because it has a nice theory, but it actually also works in practice. I'm going to show you next. So
okay,
yes.
so actually, there's one more question, then I'll move on. So there's a couple of questions. Okay, so there's just one question about how the Fisher divergence is related to like the mutual information or KL divergence. So I think this is just maybe a couple of quick comments related to your GAN comment and log likelihood, information theory, just comparing the scoring rule.
Yeah, so it's a different way basically of comparing probability distributions. When you train by maximum likelihood, you're basically minimizing KL divergence, and you can think of it as basically trying to compress the data. When you're optimizing this Fisher divergence, you're basically comparing probability distributions in a different way. There is a whole field called things called scoring rules, which are basically you can actually motivate them from a Bayesian decision theory perspective. And this is basically a different way of comparing probability distributions, and it's proper in the sense that basically as this kind of these two bullets say somewhat informally, it's going to be zero if and only if the two distributions are the same, which means
okay.
that
Okay, great. So I'll suggest that Stefano proceeds. There's a couple more questions, but you can take them. We can take them at the end, and I think some of these might get resolved as you start seeing the details of the algorithm.
Perfect. All right. So the first thing to address is how do we actually evaluate this objective function, or let alone optimize it? And as Shan was saying, the challenge is that the first term here is pretty complicated because it's the gradient with respect to x of log p of x, and p of x here is the true underlying data generating process, right? And recall the settings that we have samples from it, but we definitely don't know. We definitely don't have an analytic expression for p of x, and so it seems like there's no way we can even compute the first term. And the nice thing is that what you can do is you can do integration by parts. It turns out it's actually not too hard to see. If you look at the one-dimensional case and you expand the square, you're going to get a term which basically this squared, which does not depend on theta. You're going to get this term squared, which is easy to deal with, and then you have the double product. You apply integration by parts to that, and it turns out that it can be written to an equivalent expression up to a constant, where basically, which basically does not depend anymore on this nasty term that we don't know how to compute. And it turns out that basically this expression is equal up to a constant to this expression under some conditions. Basically, you need to be able to use integration by parts. And the nice thing is that this expression here basically does not involve terms that we don't know how to compute anymore. It's an expectation with respect to the true data generating process of something which is basically depends on our model. It's like a norm of the output of our model. It's easy to compute. And then we have the trace of the Jacobian of, again, our model as theta, which something that we hopefully are able to compute, for example, using automatic differentiation. And in particular, this is called the score matching objective. It's not something we came up with. And it also admits a sample average approximation. If you have a set of ID samples from P of X, you have a training set, you can approximate this expectation with a sample average. And this becomes an objective that you can evaluate, and you can actually also optimize as a function of theta. And intuitively, what is this saying? Well, this is saying that we're trying to choose our vector field of gradients such that the data points xi, such that the gradients are small or zero at each xi. So we wanted the xi's to be stationary points. And then we're looking at this trace of the Jacobian, which is kind of like looking at it's kind of like a Hessian, and we're basically looking at the second derivatives, and we're trying to make sure that these xi's, these data points, are not only stationary points, but they're actually local maxima of the true underlying density. And so it's a fairly natural kind of like objective if you look at it. For what we're trying to do. We're trying to find an S theta such that the gradient is small at each data point, and it's also kind of like a local maxima at each xi. And now, in principle, this is an objective that we can evaluate and we can optimize as a function of theta.
Can I view? Quick question. So, can I view the one of those two terms like a regularizer? And which one would that be? Because I'm not convinced it's the first one is the regularizer. Is it the trace that's the regularizer or the? The first.
I would think of the trace as the regularizer.
Yeah. Okay. Okay. That makes more sense.
So for example, we could use a neural network to model this score. Now this is a vector valued function. So you feed in x and it will output a vector, which is basically the estimated gradient at that point. And we need to do two things. We need to compute the norm of the output, which is of course easy. And then we need to compute the trace of the Jacobian of this object. And so to compute the first term, that's easy. You basically do a forward pass. You compute all the outputs, and then you compute the norm. So that's easy. Now, to compute the trace of the Jacobian, well, the definition of the Jacobian is basically this matrix of partial derivatives. To get the trace, we basically need to compute all the elements of the diagonal, and we have to sum them up. So to compute the first one, we basically need to compute that output, and then we need to compute the partial derivative with respect to the first input. To compute the second term on the diagonal, we need to compute the second output, and we need to compute the partial derivative with respect to the second input. And then we need to compute the third output and the partial derivative with respect to the third input. And so naively, this would require order D backpropagations. And so although it's doable, it's actually pretty expensive to do in practice because you would have to do this at training time for every data point. And so it's actually pretty expensive to evaluate this term exactly. And so what we can do is we can try to make this more scalable by using a classic idea, which is to basically do some kind of random projection. And the intuition is that one-dimensional problems should be easier. And so we can try to project this vector field of scores onto random directions, right? Recall our original objective was to try to match these two vector fields, our model with the true underlying vector field. And so what we can try to do is we can try to pick a couple of random directions, like this one and this one. We can project these vector fields along these two random directions, and we can try to match the projected vector field scores. Mathematically, this is something we call the sliced Fisher divergence. It's basically the same thing we had before, except that now we pick directions randomly with respect to a distribution PV, and we project the estimated score and the true score along the direction V, and then we, just like before, basically we compute the average over the whole space of the square difference of these two now one-dimensional vector fields. And just like before, well, it looks like there is a term that we don't know how to compute, which is the gradient of the true data generating process. But just like before, it turns out that you can do integration by parts, and it reduces to something that basically only depends on things we know how to compute. Basically, that only depends on our model, the gradient of the log density or our score model. And basically, we have one term which is easy to compute, which is where's my mouse here, which is just basically just like the norm of the output of the network before, except that now it's along a random direction V. And the nice thing is that now the first term is basically a Hessian vector or dot product, which is something that turns out can also be evaluated efficiently, basically just using two backpropagations, because these are basically directional derivatives. And so it turns out that this object can also be evaluated efficiently. And so we have a new objective, which we can estimate, just like before, using a finite number of samples from PV, which is this noise distribution, and P data. And there is a certain flexibility in choosing the way these random directions. You can use normals, you can use Rademacher distribution, you can work out the variance, and it turns out Rademacher is strictly better than Gaussian. And you can also do variance reduction by basically taking more projections. The more projections you take, the more expensive it gets, but the more accurate basically you're comparing the two vector fields. And you can also do integration, analytically integrate some of the terms. And it turns out that in that case, you get something you basically get something called the Hutchinson trace estimator, which is something you might have seen before, which is another way of approximating the trace of a matrix using some sort of.
Okay, sorry, and just to be clear, I missed something. So the P theta, this is related to S theta by just like the Gibbs, the softmax distribution, or?
Oh, good question. So I unfortunately changed my notation here. I realize now S theta is basically just this. S theta is just the gradient of log P theta.
Oh, so it's the gradient, yeah. So it's not the so it's the gradient of, and then if you just plug that in, you'll get the second term being the trace term. This is just like a homework kind of thing or something.
So yeah, so the trace term you don't have it anymore. That's the nice thing here. The trace term is basically replaced by this term here, which is basically just it's basically like an approximation to the trace because you're.
Oh, I see. Okay, I see. Okay. So it's a sorry, the changing notation. So P theta is S theta is the grad of log P theta, and then you have this approximation. Okay, that makes sense.
Yes. And so you can work, if you have an energy-based model, you might work directly with P theta, and then your vector field of scores is something you compute by taking this gradient, or you can directly model the gradient. There are two choices, both are fine, and that's why, but I have my notation a little bit mixed up here. Other questions?
I think we're good for questions.
All right, so turns out that this objective has some good properties. We can prove that it's consistent under some, it's kind of like the standard assumptions for consistency of this sort of estimators. And we can also prove asymptotic normality. We can actually also work out the variance, which is nice because as far as I know, at least we couldn't find published results on the asymptotic normality of score matching. And the good thing about this is that it scales much better than basic score matching. Coming back to the question I was asked before, whether this scales to high dimensions, that's exactly what we want to do. We want to be able to apply this method to objects which are high dimensional, like images. And if you were to use standard score matching, basically just evaluating the objective will scale roughly linearly in the number of dimensions, and at some point basically you just run out of memory and it doesn't work anymore. Well, if you use this sliced version where you take random projections, then it's almost independent on the dimensionality of your data, and so it scales much better with respect to the data dimensionality, which is what we really care about. And the nice thing is that it works well. I'm not going to talk too much about this kind of experiments, but if you try to fit these things called deep kernel exponential families, which have some kind of energy-based models with an intractable partition function, it turns out that by using slice score matching, you can basically get roughly the same results as what you would get if you were to use the true score matching objective. But as we've seen before, it's much faster because
actually, so there's one question which would make sense now. So there's a question of, does the estimator have high variance in regions of space with low density? And this is a good question. Let me just add to that question in thinking about this as kind of a bias variance trade-off based on the parametric class. So just broaden that question a little.
Yeah.
How to think about what's the issues in the low density regions.
So we'll get to that. In fact, coming up soon on exactly that's one of the problems, and we'll talk about how to fix it. And so basically, that's kind of like the pipeline. We have samples from a data distribution. We come up with an estimate of the underlying vector field of scores. And then using slice score matching, or you can use other techniques, it turns out. And then what we can do is we can try to use this vector field of scores to actually produce samples, right? At the end of the day, maybe what we want to do is we want to generate new images, so that look like the ones we have in the training set. And how do we do that? Well, intuitively, what you can do is once you have this vector field of scores, is you kind of like can follow the gradients and try to move towards high probability regions. And it turns out that if you just follow the gradient, well, that's not going to produce samples. It will just take you to some kind of local optimum. But there is a way to actually produce samples. And basically what you do is you follow the gradients, but you add a little bit of noise. And it's called measurement dynamics. Effectively, it's a relatively simple algorithm where what you do is you initialize your sample somehow based on an initial distribution. And then what you do is you basically follow the gradient, you do gradient descent, and you add a little bit of Gaussian noise at every step. And under some conditions, you can show that this will actually produce samples from the underlying distribution. And note that the only thing that we need is this vector field of scores, which we can estimate using score matching or slice score matching. And so that's kind of like the pipeline. You start with samples, you estimate the vector field of scores, and then you run Langevin dynamics to produce new samples. And now we get to the issues when you try to apply this to when we initially try to apply this to, let's say, image data sets, and we'll get to the issue of the variance. There are several issues. One that is that it turns out that it's believed that many real-world data sets actually lie on some kind of low-dimensional manifold, or approximately lie on some low-dimensional manifold. And if that happens, then the data score is not even well defined. And intuitively, you can kind of imagine a density, which is sort of a ring. And as you make the ring thinner and thinner, as kind of like the data lies on a little manifold inside this two-dimensional space, you see the magnitude of these gradients keep growing, and eventually it explodes. Right? Intuitively, it's not even a well-defined object if the data is lying on a low-dimensional manifold. And this is actually reasonably true in practice. As you know, if you take real-world data sets like MNIST, then you fit it just with PCA, which is kind of like trying to fit a linear manifold to the data. You can see that, let's say, with 595 dimensions, you can get a very good approximation to MNIST, almost indistinguishable. If you take a sample and you project it on the PCA manifold, the samples the images look identical, which basically means that indeed maybe this manifold hypothesis is approximately true in practice. If you use other data sets, again, you see that with a relatively small number of dimensions, maybe 2,000 dimensions, you can get almost you lose very little information about the original images. And indeed, in practice, if you, let's say, try to use score estimation on CIFAR-10, you're going to see a loss function which which is very, very, very unstable, and learning doesn't actually work. Another issue which was brought up by the question is that the score can be very inaccurate in low-density data regions. Right? You can imagine this process where we get samples from the data. And we're sort of like trying to, by optimizing this objective up here, which is our Fisher divergence, we're kind of like trying to figure out in which direction we should change our data point to increase its density. And what happens is that most of the data points are going to be close to the high density regions. But we don't get a whole lot of signal, a whole lot of information about what's the right direction to change our data points when we're far away from the high density regions, right? Most of our data points are going to be close to the modes. That's where we're going to get a lot of signal because our estimator is going to be based on samples, and we don't get a whole lot of information about what happens in here. The third, and indeed, you can see that this really happens in practice. Here is an example where on this toy 2D data set, these are the true data scores. These are the estimated data scores from samples. And you can see that it's pretty accurate in the corners, close to the modes. But far away from the modes, the true vector field is quite different from the one estimated from score matching. And so indeed, we can get good signal close to the high density data regions, but we don't know much about what is the right direction to change our data points when we're far away. And the third issue is that there could be the Langevin dynamics could mix very slow or not mix at all. And you can see this here. Imagine that your data distribution is a mixture of two distributions with disjoint supports. So you have P1, which has this support, and P2 with this support. And imagine that there is a mixing coefficient pi. So it's a mixture of P1 and P2 with coefficient pi. Now, if you look at the score is going to be the gradient of the log. And so basically, you can see that in this region, the score is going to be just the gradient of log P1 of x. And in dependent pi, because when you take the log of pi is just going to be a constant. And in this region, the score is just going to be the gradient of log P2 of x. And so you see that basically the score does not even depend on pi. And so this is problematic because basically what this means is that there is no way to recover the right weight of the two mixture components just by looking at the score. And this is, of course, kind of like a little bit contrived example where we're assuming that the modes have separate supports, but kind of like that's issue in practice when the modes are separated by low density regions. It might be very hard for the Langevin dynamics to go from one mode to the other mode while following the gradients. And indeed, that's something that happens in practice. If you try it on this simple toy example, IID samples would look like this. If you try to use Langevin dynamics, it's kind of like sampling where basically this mixture has more weight than this mixture. So you get more samples up here than down here if you were to sample IID. If you were to use Langevin dynamics, you get roughly the same number of samples here and here. Because basically our Langevin dynamics would take an extremely long time to mix and actually go from one mode to the other mode. So you see too many samples down there. So before I move on into talking about our solution, questions on the issues that we've identified, the three issues?
I think you hit all of the questions.
Perfect. All right. So I think we're also pretty short on time. So luckily, the solution is going to be very simple.
For time, I think we can go till 3 because there's a break between them, so we can just start questions at 3. So.
Oh, all right. So it turns out the solution is actually very simple. The solution we came up with is to basically just perturb the data by adding some Gaussian noise. And remember, one issue is that, the data is actually lying on this low dimensional manifold. If you do PCA, basically the data points, they don't, if you look at these images and you PCA project them, they don't really change, which means that they are very, very close to a linear manifold, and maybe something even lower dimensional if you're allowing nonlinear manifolds. If we want to fix this problem, what we can do is we can add noise to each of these data points so that then the distribution becomes supported on the whole space. And indeed, if you just add a little bit of noise, remember, if you were to train just using slice score matching on CIFAR 10, you would see this very, very unstable learning curve. But if you add just a little bit of Gaussian noise to the images, you get something that is much more stable. If you think about the problem of not getting signal in low density data regions, again, this problem can be solved if you add a sufficiently large amount of noise, right? If you add a lot of noise, then the distribution will be supported everywhere. And so when we look at our samples, we're going to be able to get signal from everywhere in the space. And of course, then there is a trade-off here, because if you add a lot of noise, then you're corrupting the true underlying data distribution too much. And so what you want to do is you want to consider multiple levels of noise. So you might start with a lot of noise, a little bit less noise, a little bit less noise, and eventually a tiny little bit of noise that basically doesn't change the data distribution at all. And we can try to estimate the vector field of scores corresponding to all these data distributions perturbed by various amounts of noise. And the idea is that by doing it, we're going to be able to get signal about what happens both close to the data manifold and far away from the data manifold. And so
there's a question, what space is this, in pixel space?
In what space?
What space is this? Is this noise in pixel space?
Yes, this is in pixel space. Basically, then what you can do is you can sample using this vector field of scores that we've estimated for different levels of noise sequentially using Langevin dynamics. And so we can start with a distribution that has been perturbed by a lot of noise. In this case, Langevin dynamic will probably mix reasonably quickly, and we have a pretty good information about what the vector field of gradients look like, and we can run our Langevin dynamics. Then we can use these particles to initialize a second Markov chain where we use a smaller amount of noise. Let's see if this works. And we keep going, and then we look at an even smaller amount of noise, and we once again run our Langevin dynamics by initializing it with particles come from the previous Markov chain, and then we end up with samples that are hopefully from a distribution that is very similar to the true underlying one, because we've been adding very, very small amount of noise. So sigma L kind of like is going to be very, very small. And so that's kind of like the picture. Like, remember, if we were to use Langevin dynamics on this mixture model, you get too many samples down here. If you are using annealed Langevin dynamics, then this problem is basically solved. If you use multiple noise levels, then you see that you end up with a solution where you get many more samples up here than down here. So we're actually improving the mixing behavior of the Langevin dynamics. And so practically, what we do is we consider multiple noise levels, and for different noise levels, there's going to be a different vector field of scores. And for scalability, we basically use a single neural network that will try to jointly estimate this vector field of scores for different noise levels. And so you can think of the noise level as being an extra input to your neural network. And so, but it's a single model is kind of like amortized to produce this vector field of scores for different noise intensity. And really, it's going to be easier to estimate the vector field of score with high noise, but the problem is that then, let's say you were to sample from that, you would produce images that have been corrupted by a lot of noise. On the other hand, the final noise level, which is very, very small, it has the issues that we talked about before, but the images are clean because you're adding very, very small noise. But by jointly estimating all of them, we can kind of like get a good trade-off, and we can sort of like get around the issues, the pitfalls that we discussed before. And as I promised, here are some examples of how this works if you try it on the real-world data sets. These are fairly high-dimensional image data sets. And here you see what happens if you basically run this procedure. You start with random noise, and then you follow this vector field of scores to actually try to sample from the true underlying distribution. using Lagrangian dynamics. You're using these multiple chains at different noise that have been trained on different noise intensities. And you can see the samples look pretty good. If you believe in the this kind of sample quality metrics like inception and FID score, you see that on CIFAR 10, for example, you get an inception score which is higher than all the GAN models, by a little bit. It's not too far from the kind of inception scores that you would get if you were to look at class conditional models. So this is an easier problem where you have class information. We get 8.91, which is not too far from the 9.22 that you would get if you were to use a class conditional big GAN. And it's better than things like SGAN and other pretty, pretty good GAN models that people have produced. In terms of FID scores, we're slightly worse than the best GAN models, but it's again not too far away, which I think it's pretty remarkable if you think that how many years of architecture tuning and hyperparameter tuning went into GANs, and we were able with a single graduate student to basically get images using a different kind of training objective that are actually pretty good, and even visually, I mean, they look very comparably to what you would get using GANs. And let me maybe talk a bit about other sort of experiments that we did to check, for example, whether the model was actually memorizing the training set. So we did some experiments doing nearest neighbors. So we looked at a sample from the model, and then we looked at the nearest neighbors in the data set. And generally, it seemed like, so this is the sample from the model.
So some we can move to the end, but there's a question now about that I was wondering about too. How do you think about mode collapse, and looking at like birthday paradox would be the simplest way, is what Sanjeev suggests. But yeah, just in general, how do you think about overfitting and mode collapse here?
So mode collapse shouldn't happen in the sense that if you believe it's a proper scoring rule, so it shouldn't happen. Whether it's actually overfitting, this is kind of like the empirical results that we tried to check whether it's really overfitting to the training set, that it could be doing that. It doesn't seem like it's doing that. If you look at nearest neighbors, so you just take a sample from the model, you look at the closest things that you've used in training, you don't get the same thing. Here are some examples. This is in pixel space. If you try to take nearest neighbors in a feature space from a pre-trained model, again, if you look at the first column, which is the sample from the model, and you look at the closest, 10 nearest neighbors from the data set, you don't get an exact match, which is kind of like suggesting that it's not overfitting. It's not just
right. I guess they aren't quite the same. Mode collapse is a bit different, but than overfitting. But yeah.
Yeah. Yeah. I mean, I think to some extent these metrics capture a little bit of that, but we didn't experience it. And I think it's not like, again, I don't think there's an incentive to do mode collapse based on because it's a proper scoring rule.
Yes.
Does that answer your question? And the other thing that we did a little bit heuristically is to try to do in painting. So if you take an image, this is the true image in the data set, and then you remove half of it, and you try to complete it, you get reasonable things, which is again suggesting that it's learned something, and it's not necessarily exactly the one that it has seen in the training set. Some of the images, there is some variation in the kind of ways that it completes an image, which is sort of suggesting again that it's really learned something about the structure of these images through this model. Okay, maybe before I move into the last section, any other questions on the evaluation or how the method works?
So one more question. So this is about scaling up to higher resolution images, and kind of how have you looked at that? And there's a question about a concern, which is what happens, for high-res images.
Yeah, that's a great question. This is the highest image. That's something that we're working on. We're getting some pretty good results, but it's at the moment it's not yet published. There are some issues in terms of like figuring out what is the right architecture for the score model on high dimensional images. When we use the one from this Nurip's paper, it turns out that it produces some strange color schemes, and that's something we're trying to work around. But I mean, these are reasonably high dimensional, but not super high dimensional. That I agree. It's at the moment it's a limitation of the approach, and something that we're hoping to fix soon. Other questions?
Is there some connection between annealing the noise for SGLD and tempering the distribution? Which thank you.
Yeah,
that's basically
that's another
you
way
answered that. Yeah.
All right, so if there are no more questions, I just want to talk a little bit about evaluation. I guess I've shown you some metrics, some ways of trying to kind of like heuristically evaluate these generative models. But I think it's actually a pretty hard problem thinking about, what does generalization actually mean for these sort of generative models? And kind of like the toy question would be, like, imagine that you train one of these models, your favorite GAN or this noise, our score matching model, on a data set where you have red cars, blue cars, and red buses, right? And then the question is, let's say that in your training set there is no blue bus, but would you want your model to produce samples of blue buses? And or more concretely, maybe you can use the clever data set, and you could produce a training set where all the images have two objects, and the objects might have different shapes, different colors, but all the images in your training set have two objects. And then you train your generative model, and then you look at the samples, and you can ask, would you want your generative model to produce images with two samples, or would you want it to produce images with, let's say, maybe two objects, three objects, one object, where there's a varying number of objects? And I don't know whether this works in this virtual setting, but how many you can? I'd be curious to know how many of you think that the answer is, let's say, if you train a GAN, a state-of-the-art GAN on this kind of data set, would you think that the samples are like A, so all the samples have two objects, or like B, where there's a varying number of objects? And it's not even clear what you would want, right? And I'll let you think about this for a few seconds and think about what you think is your guess of what would happen. We did these experiments. We tried many generative models, GANs, autoregressive, VAEs, other things.
D. That's right. The first person who answered was D. All right. He's right. Ian is right. Good job.
Yes, and in fact, good job. Yes, and indeed, we found that it tends to generalize across that dimension. It tends to produce images with varying number of objects. Whether that's a good thing or not, but you can basically project your images along this dimension, this semantically meaningful dimension, which is how many objects the image contains. You might have a training distribution where all the images have exactly two objects, and then you can look at what is the generated distribution if you project it on that dimension. And what turns out, if you look at these models with reasonable hyperparameter settings, you get that they generalize, produce this kind of like log normal shaped distribution, where most of the images have two objects, but some of three, some of one, maybe some of four objects. And there's this interesting effect.
We should just plan on wrapping up and taking questions.
Yes, all right. And so turns out that we've explored this kind of setting, and you're gonna see some interesting behaviors in terms of like the way it generalizes. For example, if all your training images of 2 objects and 4 objects, and you look at the distribution of the generated images, you'll find that most of the images actually have 3 objects, even though the model hasn't seen any image with 3 objects, which is pretty surprising to me. We looked at different other features like color, size, location, and this is kind of like inspired by experiments that people have done in cognitive psychology, studying like the visual systems of humans. And we've tried to replicate similar experiments and looked at multiple features, like what happens, like the car and the bus and the color example. If you have spheres that are yellow and red, and cylinders that are, but the only cylinder that the model has seen is red, will it produce a yellow cylinder? And we've been able to study this empirically. We know that unbiased density estimation is impossible, and so the inductive bias is key. And unfortunately, we don't really understand how we put that into the architectures, the learning objectives that we use, the hyperparameters, and so forth. But I think it's an interesting question to explore, like exactly how do these models generalize and how do we incorporate the right inductive biases into these models. And so, yeah, I just wanted to bring it up because I think that's actually an important question to think about. How do we evaluate generalizations? What do we want? Would we even want them to produce images with a different number of objects, different colors? Obviously, some generalizations make sense, some don't, but these models have no idea about what, no common sense. They have no knowledge about the world, and so it's a mystery, kind of like at the moment, how they generalize. And so yeah, I think that was the last thing I wanted to talk about. And just to conclude, to wrap up, we've talked about score-based generative modeling, which is something I'm quite excited about because it's an alternative to GANs and to standard sort of like likelihood-based models that we've been able to get to work quite well in practice. It's principled. It doesn't require adversarial training. You don't have to sample during training, so it's very scalable. And we've shown that with this addition of noise, we've been able to get very good results comparable to GANs. And well, yeah, the final thought was that we need to think hard, I think, about evaluation and what we want these models to do. And yeah, I think that's it. I'm happy to take questions if there's time.
I'll just thank Stefano on behalf of us all for a great talk. So so I'll just start ping people on a couple of questions. So one interesting one is, any thoughts or have you tried this on language generation?
So one issue that might not be super clear is that unfortunately it only works on continuous. It works. You need to take a gradient with respect to the input dimensions. So technically speaking, it would only work on probability density functions, so continuous data, and so it's not well suited, I would say, for something like language, which is.
And another question I missed was, have you derived any formulas for the variance of this gradient estimation in your procedure?
Yes. So going back to we've been able to actually work out analytically what is the asymptotic variance when we derived the. I think I would have to go back too much. Well, when we derived the asymptotic normality result, we've actually derived the variance, and we've been able, for example, to compare the variance that you get from using a Rademacher distribution or a Gaussian distribution, and we've been able to show that analytically, for example, Rademacher is better, and how it depends on the number of projections that you take. So yeah, we've been able to get some decent theory about and then some good theoretical understanding.
Actually, right. So there's two related questions that seem kind of interesting. So you could potentially, get around this generation by working in the embedding space for language modeling, because that's continuous. I guess, the issue there is how you go back from the embedding space to the words, but maybe there's some sparse decoding. But yeah, anyway, this is one.
Yeah, that's a good point. Yeah, that's something we haven't tried, but yeah, it'd be interesting to see whether it works. There is also like variants of score matching that are actually derived discrete distributions. So maybe those variants.
Okay, so let's see. So well, we definitely have a little more time, so let's just take a few more questions. So there's one more question on. I mean, obviously people can go, but I think there's a lot of interesting questions. So, so someone, was thank you again for the talk. And the question was, is the bus/yellow cinder cinder generated by the model in your experiments?
So the bus, no, that was sort of like just a thought experiment. The actual, these objects, this is, we use Clever, and so these are the cylinders and the spheres. These are actual data sets. These are actually trained. So we use Clever, where we have like control over this kind of like axes, like number of objects, color, shapes, positions. And we've been able to do, I mean, this is of course synthetic, but we've been able to do very controlled experiments in terms of like what happens as we change various things on the training distribution, kind of like projecting along these axes. We don't understand, these objects are too high dimensional. It's too hard to think about what they do and what generalization means in this context. But at least basically drawing inspiration from how people have been thinking about our own visual system in cognitive psychology, we basically tried to see, well, let's think of it as a black box. Let's project these high dimensional objects along directions that are meaningful, like the number of objects, color, shape, and let's see what happens. And we found some interesting empirical results, but we don't have a theoretical explanation for why these results, why they do these things, and we don't understand what is the key inductive bias that we've put in so that it does B instead of A. Because to me, it seems like both are reasonable, and there's no good reason for choosing B versus A. You have, even if you think about like a certain number of features that you care about, there's going to be a combinatorial number of different combinations of the features. Your training set is always going to be finite. You only get to see a subset of them, all the combinations of, let's say, shape, color, numerosity. And so the model needs to somehow extrapolate and figure out what is possible and what is not. And we don't know.
I have one more question. So going back to this issue of scoring rules, and kind of related to mode collapse, not quite, but to this point that you're training on some objective and you don't find it to have have things like mode collapse. Now, there's this there are these what is it, the flow GAMs or the real MVP sort of models where you explicitly parameterize the network so you can actually compute the derivative of the log likelihood function. And those have this nice property that you get like legitimate log likelihood scores, so you can get actual code costs for images. And again, for me, like this class of like the closer you are to probabilities, this feels like very nice. And how would you compare? What's your thinking compared to like the sort of real MVP approaches and in the space of cost functions that you can optimize efficiently?
Yeah, I'm also very excited about like flow models and like invertible neural networks. I think it boils down to, I mean, even there, like you do need to make sure that these neural networks are convertible, and that poses, and you need to be able to compute the determinant, the Jacobian, and so basically you're putting a lot of constraints on the models that you can use, and that's always a problem in terms of the kind of performance that you get. And there's always this trade-off between flexibility and tractability. And our thinking was, well, maybe by working at the level of scores, we can get different kinds of trade-offs because there are not that many constraints that we have to put on the score function or on the energy function if you have an energy-based model. And so I'm very excited about flow models, other kinds of same like probabilistic approaches where we understand there's a proper scoring rule, we understand what they're doing. You mentioned flow GANs. I think when we tried that, it was like, again, well, that would work, and it turns out that there's always like this kind of trade-off between getting good likelihoods and getting good samples, and those two things are not correlated. And yeah, I think is score matching more correlated with sample quality? Maybe, maybe not. I think also a lot has to do with coming up with the right architectures, figuring out what are the right sort of like inductive biases. And similarly for invertible models, it's not like any invertible neural network will magically work. And so I think there is more to just the objective function that you use that matters for performance. Other questions?